Hello and welcome to this new video in our series dedicated to reviewing scientific articles. Today we're going to talk about the application of quantum computing to finance. To do so, we will be looking at the article titled Quantum Computing for Finance. This article was written by Jilan Eman, Koji Gugin, Zhayuan Liu, Yu Sun, Alexei Galda, Lia Safro, Marco Pistoia, and Yuri Alexeyev. The author come from a variety of institutions, including JP Morgan Chase, the University of Chicago, Fujitsu Research of America, the University of Delaware. The company maintains high and Argonne National Laboratory. This article, which is actually a review paper, presents the state of the art in the use of quantum computing in the field of finance. The author focused on three main areas: stochastic modeling, optimization, and finally machine learning. We will follow this structure as we go through the content of the article together. Also, the article contains a few terms and expressions specific to finance, which is to be expected given the topic. However, in this video, we will try to focus primarily on the quantum algorithms themselves and what they actually do, without necessarily dive into how they integrate into the full finance workflow, as that would require a deep dive into the financial side of quantum computing, which is beyond the scope of this video. Stochastic modeling is widely used in finance. Indeed, quantities such as stock price, interest rate, and associated volatility are modeled as stochastic process. Overall, the goal is to maximize return while minimizing risk. The author outlined two approaches to tackle the stochastic process in quantum framework, both inspired by classical method. The first involves developing a quantum version of the Monte Carlo method. The second consists in solving using a quantum algorithm the differential equation that govern the stochastic process. A derivative is a financial product whose value depends on the price of another underlying financial asset, which is typically modeled as a stochastic process. Classically, the expected payoff of such a product is estimated using Monte Carlo integration, with an error that scales as grid O of sigma square divided by epsilon square, where sigma square is the variance of the payoff and epsilon is the target estimation error. The article introduces a quantum version, quantum Monte Carlo integration, which can produce an epsilon estimate of the price using only grid O of sigma divided by epsilon quantum sampler, with constant success probability. This quantum approach relies on quantum amplitude estimation. It offers a quadratic speedup over the classical method. However, the article notes that this advantage could be reduced or even lost when the overhead of quantum error correction is taken into account. A variant of classical Monte Carlo integration, known as quasi-Monte Carlo integration, can achieve performance comparable to that of the quantum approach. In other words, the quadratic speedup expected from quantum Monte Carlo integration can, under certain conditions, be attained using classical method. Sensitive of the derivative, this quantity measures the risk associated with a financial derivative. In practice, it corresponds to the gradient of the derivative price. Therefore, quantum evaluation of this gradient have been considered. The paper specifically highlights a study proposing an algorithm that accelerates the classical bump and reprise method used for this calculation. The paper notes that other work based in certain regularity assumption evaluate sensitivity using automatic differentiation. A quantum enhancement of this approach has also been explored with an amplitude estimation algorithm. About quantum method for differential equation-based pricing and risk analysis. The second technique present in the paper regarding financial derivatives is the resolution of partial differential equation. Associated with stochastic differential equation, the paper explores various approaches for this. Since These type of equations are commonly approached classically using finite difference method. One approach is to combine a finite differential-based method with a quantum linear system algorithm. The paper clarified that such a combination allows for exponential acceleration in solving PDE. However, when considering the process of extracting quantum information into classical information, the performance ends up being similar to that of Monte Carlo method. For second-order equations that have the same structure as the Schrödinger equation, the simulation of the Hamiltonian is performed to obtain this dynamic associated with the partial differential equation. Quantum variational algorithms have also been used to solve PDE. The paper cites several works on equations that appear in finance: the Black-Scholes equation, the Feynman-Kac equation, the Hamilton-Jacobi-Bellman equation. A final approach discussed in the paper involves using quantum neural network where the variational parameters are updated through gradient descent to satisfy the partial differential equation. Okay, it was a presentation on which aspect on how quantum computing is used for stochastic modeling in finance. Now we talk about optimization using using a quantum algorithm for optimization in finance. Many problems in finance can be reduced to optimization problems. The article characterized them into three types: continuous variable optimization, discrete variable optimization, and dynamic programming. Quantum methods for continuous optimization. All classical methods offer good performance for this type of optimization problem. Some quantum approaches with speed-up expectation have been proposed for certain aspects of computation. Some of the problems present include cash flow management, arbitrage detection, and portfolio optimization. Quantum basic linear algebra subroutine algorithm, which offer computational speed-up in the worst-case scenario. We also have a quantum version of the quantum version of the matrix multiplicative way algorithm, which achieve a quadratic improvement in complexity. A quantum Gibbs sampling introduced for derivative pricing. Also, a quantum amplitude amplification used to train a kernel classifier. These methods mainly serve as subroutine, which in classical optimization method. The author also highlights three key limitations to quantum advantage in continuous variable convex optimization problem. First, the polynomial dependence of quantum basic linear algebra subroutine method on matrix conditioning, which is not always present in the classical case. The second limitation is the cost of extracting quantum data into classical data, which must be accounted. The last constraint is the need for data access on superposition state, which is only efficient for space matrix. For quantum method for discrete optimization, the author note that portfolio optimization is more often formulated as a binary optimization problem, typically categorized as a maximum independent set problem. The article presents various quantum approaches that tackle this class of problem. We have a quantum worksheet to simulate symmetric Markov chain, simulated annealing adapt to solve combinational problem, Grover algorithm for unstructured search, quantum heuristic algorithm including quantum approximate optimization algorithm, and variational quantum eigensolver. However, some limitations remain. Variational algorithms often suffer from challenge in tuning both variational parameters and hyperparameters, which can themselves be NP-hard problems. Furthermore, while quantum annealing benefits from quantum tunneling effect, it is not always guaranteed that the physical conditions are met for tunneling to be effective for given potential. Additionally, mapping continuous variable to discrete ones can become computationally expensive. In the last kind of optimization, we let us talk about dynamic programming. Dynamic programming problems are also common in finance, particularly in applications like American option pricing and the structuring of collateralized mortgage obligation. Although no specific quantum algorithm has been proposed for this exact class of problems, the article reference research focused on reducing the exponential complexity associated with dynamic programming for various NP complex. Now, let's dive into one of the most promising and fast-growing area discussed in this paper, machine learning and how quantum computing could impact its role in finance. Machine learning is already a cornerstone in the finance industry. It's used for everything from detecting market patterns and fraud to classify financial news and optimizing portfolio. So naturally, the big question is, can quantum computing do it better? The paper breaks quantum machine learning into two main categories. First, quantum accelerate classical technique, which often rely on quantum linear algebra tool or quantum basic linear algebra subroutine. The second part is quantum native model like quantum neural network and quantum kernel method that aim to be fundamentally different from anything classical. The first type usually need fault-tolerant quantum computer and struggle with issue like loading classical data into quantum memory. The second type may work with near-term device, but whether they actually outperform classical method, especially on classical problem, is still an open question. Quantum algorithm for regression, a key task in forecasting and asset pricing, have been explored, notably explored. Notably, least square regression has been reformulated as a quantum problem, and quantum annealing has even been used to solve it. There are also proposals for using Gaussian process regression with quantum linear algebra that could lead to exponential speedup, though only under certain conditions. Next up is classification, which is central to applications like credit risk evaluation and fraud detection. Quantum enhanced version of support vector machine, nearest neighbor classifier, and quantum neural network have been explored. Some of these methods show small polynomial or quadratic speedup, but they often depend on very specific assumptions or require access to quantum example, which is still a technological hurdle. In terms of boosting, which is about improving weak linear into strong one, there are a few quantum proposals like quantized Ada boost and smooth boost that reduce the dependence of VC dimension, but again, they usually require quantum state preparation of the training data, which is far from trivial. There is also quantum Q-boost, a hybrid method using quantum optimization to select combination of weak classifier. It has already been applied to financial risk detection, so that is one concrete use case. For clustering, which help uncover structure in data, like identify group of correlated stock, quantum version of k-means and spectral clustering have been proposed. These show improved scaling in some settings and even NISQ compatible version exist. In some cases, quantum clustering can outperform classical approach if the problem meets specific requirements like sparsity or low error correction tolerance. Now to one of the most exciting parts, generative learning. Quantum generative model like the quantum CQ-bound machine and quantum adversarial network aim to simulate probability distribution, which is perfect for financial simulation and derivative pricing. These models exploit the natural probability nature of quantum mechanics, and early results suggest they could rival or even outperform classical models like the Boltzmann machine. In finance, feature extraction must be not only efficient but explainable. That is crucial for regulatory reasons. Quantum PCA has been proposed, but extracting useful classical information from quantum output remains a challenge. There is also growing interest in topological data analysis and quantum combinatorial feature selection, which could become useful tools down the road. Reinforcement learning is already used in trading, pricing, and portfolio management. Quantum algorithms for reinforcement learning explore how to use Grover search or quantum gradient estimation to amplify good strategy and speed up learning. It is early day, but this is an exciting area where the adaptability of quantum systems may shine. And finally, the paper touch on the quantized algorithm, classical algorithm inspired by quantum ones. These have, in some cases, on the might highly claim of exponential quantum speedup. However, they also show how thinking quantum can still benefit classical finance by sparking new algorithmic ideas. To wrap it up, this review paints a clear picture. Quantum computing holds promise for finance, especially in machine learning, but there's still a long road ahead. Most current algorithms either require idealized hardware or make strong assumptions. That said, quantum machine learning could still bring significant improvement, particularly in sampling, simulation, and optimization. Once the hardware catch up, so why we are not there yet, research like this help chart the path forward. Conclude this review, the author unpacks the promising, but still uncertain, role of quantum computing in finance. While we have already seen potential benefit in areas like stochastic modeling, optimization, and quantum machine learning, there is still no fully demonstrated end-to-end quantum advantage for practical financial application. Yet, the financial industry, due to its constant need for speed and accuracy, could be one of the earliest and most significant adopters of quantum computing. For instance, risk evaluation in derivative trading must be done quickly and precisely, especially in volatile market. Fraud detection is another case where timely insight can prevent both financial and reputational damage. These use cases make the financial sector a prime candidate to benefit from quantum speedup. However, the author also highlight the technical challenge that remain but particularly on the hardware side. Current limitation is in quantum memory, state preparation, and gate operation speed must be overcome to make quantum algorithm truly competitive. They point out that native multi-qubit gate, more efficient arithmetic operation, and faster clock speed would drastically improve the feasibility and performance of financial quantum algorithms. In short, there is tremendous potential, but realizing it will require significant advance in both quantum hardware and software. Thank you for watching this presentation. I hope it gave you a clear overview of the current state of future outlook of quantum computing in finance. If you enjoyed it, feel free to like, share, and subscribe for more content on quantum technologies and their real-world applications. See you next time.